This conference will now be recorded.
Very good evening, students. Welcome to the PYQ discussions with the physics class. So today we are going to complete the discussions on the paper JEE Main paper 2021 31st August shift 1 paper. So let us start our discussions. Let me change the color of the ink. Okay. So here this question says a capacitor of 50 microfarad is connected in a circuit shown in figure. Okay, this is the figure. The charge on the upper plate of the capacitor is dash microcoulomb. So you have to find out the charge in this upper plate. In fact, charge will be the same in the upper plate and lower plate as well, but the sign will be different. Okay, so we know, see, this is 6-volt DC battery, so there will be flow of charges through this, and this capacitor will get charged, and hence it will store some charges. And you look here, this point and this point are same for this resistor as well as this capacitor, and all three resistors are actually identical, 2 kilo ohm, 2 kilo ohm, 2 kilo ohm. Okay, so the voltage drop across each will be 2 volt, 2 volt. Okay, and across this also will be 2 volt, so that it will be total 2 volt. And since this capacitor is connected across this resistor, so we'll have potential difference across this capacitor also 2 volt. Okay, so there will be 2 volt. Okay, so when we know the voltage or potential difference across the plates and the capacitance, then what else you require to find out the charge? So you know the formula, Q is equal to C into V. V is the potential difference across the plates, and C is given. So this is microfarad, C is 50 microfarad, and this is in volt. So it will be actually 100 microcoulomb. So farad into volt will be coulomb. Okay, so it will be 100 microcoulomb. Okay, so this is 100. Okay, all right. Let us go to the next problem. This problem is also very simple problem if you can do it in cool mind. Let us see this figure. Okay, we have to find out the voltage drop across this 15 ohm resistor in the given figure. Okay, so here you look, this 12 volt battery is connected to this parallel branch as well as this 1 ohm resistance. First of all, I have to find out what is the current flowing through these two branches. At least I need to know what is the total current first. Okay, total current. And then I need to know what is I1 flowing through this branch, that will flow through this whole branch itself. Okay, so I1 and I2, that the things we can actually find out. So how do you find out that? So for that, better to find out the equivalent resistance for these two branches. Look, this is actually parallel branch 4 so 4 into 4 divided by 8, so this will be 2. So I have got 2 out of this 2. I have 2 already here in series, and this is 15 into 10 divided by 25, so this will give you 6. So look that this is 2 to 4, and 6. I have got 10 ohm resistance in the upper branch, and the lower branch I'll get here 8 into 8, sorry, 8 into 8 divided by 16. So this will give you 4 here, and this will give you, see, 12 into 12 divided by 24. So 12 to 6. So this will be actually 6. So I have got resistance in the both branches as 10 ohm. Okay, 10 ohm. So here also 10 ohm, and I have got another resistance 1 ohm, 1 ohm. So this is connected now with this 12-volt battery. Okay, 12-volt battery. Now what is the total current? See, this will give you 100 by 20. So this will actually equivalent will be, see, equivalent resistance will be then 6 divided by, sorry, 6 ohm. Okay, 6 ohm ultimately. So this is 12. So the total current which is coming out of the battery will be actually 2 volt, sorry, 2 ampere. Okay, so the total current coming out is 2 ampere, and since these two branches will have the same equivalent resistance, so through this there will be I1 will be 1 ampere and I2 will also be 1 ampere. Okay, so what I have got so far, I have got, say, I have to actually rub some of the portions so that I can show you clearly. So what I have got, I'm not rubbing the other portion, right hand side. So what I have drawn, look here, I2 and I1 I have got. See, the total current is 2 ampere, which is flowing through or coming out from the battery. And okay, so this is 1 ampere. This is also 1 ampere. So this much I know now. See, I have to find out, see, up to here, there will be 1 ampere current coming up. Okay, one I1. Then this will be again branched through these two paths. Okay, so I have to use here current division. Okay, formula for the current division of current. I have to find out current through 15 ohm. So what I have to write, the total current, that is the 1 ampere or I1 here, into the resistance, which I'm considering that one I should not write. I should write the other resistance, that is 10, divided by the total resistance, that is 10 plus 15 ohm. Okay, so this will give you the current through 15 ampere. This is actually current division formula. Okay, division of current division. Likewise, you can find out a formula for voltage division also. So here, look, because of this resistance, I am not able to do that. These two will actually have same voltage. That I am not able to do here. Obviously, these two will have same voltage. That is fine, but I cannot proceed further with this. Better to find out the current. So this will be, see, this is 1 ampere divided by, see, 1 into 10 divided by 25, which is actually 2 by 5, which is 0.4. Okay, so 0.4 ampere I have got. Now I have to find out what is the voltage across this 15 volt. Okay, sorry, 15 ohm. So current into current into resistance IR. So what is the current flowing through this 15 ohm? That is 0.4, sorry, 0.4 ampere into the resistance, that is 15. So this will be actually 6 volt. Okay, so what is the voltage? 6 volt. Okay, and this will be the answer for this question actually. Okay, so 6 volt will be the answer. So 6 volt is going, 6 volt will be the voltage drop across 15 ohm resistance. Okay, so this is all for this question. Let us go to the next problem. Okay, this problem is also very simple problem. This is from electrostatics. Let us see this problem. The two charge particles A and B having charges 20 microcoulomb and minus 5 microcoulomb respectively are held fixed with a separation of 5 centimeter. At what position a third charged particle should be placed so that it does not experience a net force? So I have got two charges, 20 microcoulomb and minus 5 microcoulomb. They're separated by 5 centimeter. So I have to get a third charge. Let us say that charge has, like that charge is small q. So I have to place this charge at a place such that there will be no net force experienced by this charge. Okay, that means, if I keep a charge, let us suppose we are placing the charge on the axis of these two charges itself, okay, in the same line. But where to put the charge? Whether I should put the charge here near to 20 microcoulomb, okay, or near to minus 5 microcoulomb. So which one is logical? Or I should put in between here somewhere. Okay, see, logically this has got more charges. See, much more. This is minus 5, this is actually 20. So this has got very large charge. So to balance the force given by this 20 microcoulomb charge on this, I have to somehow keep this charge in a way that this force, like the force applied by this minus 5 microcoulomb, at least becomes equal. Okay, it becomes equal at least. So for that, if I just keep near this, see, at this particular position or left side to the 20 microcoulomb, then this is actually nearby. This is, suppose this distance is less than this distance. You look here, so the charge is also less and the distance is also very large. So the coulomb force will be 1 by r square, right? It varies as 1 by r square. So the force applied on this q charge, third charge, by minus 5 microcoulomb will be really very less than the force experienced by this q charge due to 20 microcoulomb. So the logical point will be to keep the charge near to the 5 microcoulomb, minus 5 microcoulomb charge. Let me consider this distance. That means I'm keeping the charge, third charge, at the right side of minus 5 microcoulomb at a distance x, say. Okay, x. Then according to the problem, these two forces, the force applied by 20 microcoulomb will be exactly equal to the force applied by minus 5 microcoulomb, okay, on this Q charge. So I can write K Q into 20 microcoulomb divided by R square, means it is actually 5 plus this 5 plus x whole square. This will be exactly equal to the 5, the force I am taking the magnitude, 5 q into 10 to the power minus 6, k will be here, so k q divided by r square is actually x square. Now look these two things here. This q I can strike out, this k are constant, this 10 to the power minus 6 I can strike out. So what I get? See, I get 5. I can actually simplify a little bit. So 4. See, I get 4x square is equal to 5 plus x whole square, right? So from both sides, if I just take square root, I get 2x. I'm just taking the positive, plus or minus it should be, but I'm taking just positive plus. So this is 5 plus 2. Now this will give you x is equal to 5, and this is in centimeter, okay? This is in centimeter. All right. Here actually I should have written 10 to the power minus. Okay, centimeter, let it be both side. Anyway, unit will go away. Okay, so I have got now the answer. So x will be actually 5 centimeter, 5 centimeter, and that is actually right side of the charge minus 5 microcoulomb. Let us see the options. At 5 centimeter from 20 microcoulomb on the left side of the system, no, this is wrong. At 5 centimeter from minus 5 microcoulomb on the right side, it is actually true. Others will be obviously not true. Okay, so we have got B to be the correct answer for this question. Okay. Oh, I'm sorry, this is, yes, this is fine. Yeah, on the right side, yes, this is the answer. Okay, now we have got another problem. This is for an ideal gas. The instantaneous change in pressure P with volume V is given by this equation, dP by dV is equal to minus AP. So A you have to take as a constant over here, and P is the pressure, instantaneous pressure. So the question is saying that if this instantaneous pressure is P0 sometime, then this will be, volume will be 0. That means this is the boundary condition at V is equal to 0. That means where the volume is 0, the instantaneous pressure will be P0. The maximum temperature of 1 mole gas can attain is how much out of this 4 options. See, so we have to find out the temperature, maximum temperature attained by this process. Okay, so we have been given dP by dV is equal to minus AP, right? Let us do the integration. So I'll keep this dP by P here. and minus a, sorry, a dv. Okay, a dv. Now integrate it within the limit. See, when v is equal to 0, v is equal to 0, then p is equal to p0. Okay, this is the boundary condition. And let us say the final volume is v when this will be p. Okay, so this will give you, see, ln, this integration if you do, you will get ln p by p0. Okay, this p is upper limit, this is lower limit, and on the right hand side you will get a into v. So this is the thing you get. Okay, now see, from here actually we can write p is equal to p0 e to the power minus a v. This I can write, you can just check it. P is the instantaneous pressure and p0 is the pressure when the volume is 0. Now I have got the expression for the instantaneous pressure, right? Can we write PV is equal to RT for 1 mole gas? Yes, I can write this. So from here, see, if I put the value of P over here, okay, so what we will get? So P0, I'll write P0 e to the power okay, I have to find out T actually. All right, just a minute. I'll just go to the next page. So I have got this expression. Let us go ahead with this. So we know PV is equal to RT for 1 mole gas. So from here, I can write temperature T is equal to PV by R. So what is P? P we have got P0, V is there, e to the power minus A. This V is, I'll write similar, same kind of notation. Okay, so this is V divided by R. Okay, this is fine. Okay, now I have to find out what is T max. So for T max, I can write dt by dv equal to 0. Now let us find out the values of v. Okay, values of v, or sorry, I have to find out this a. I have to find out the value of a, for which I am actually going to get maximum temperature. What is the value of this a when I'm getting maximum temperature? So let us put this dt by dv is equal to 0. So this expression we know. So dt by dv, this is actually, see, if I just take derivative with respect to v, so first term to the power minus a v by r minus a p0 v by r to the power minus a v. This I have to put 0. So look, then we get, see, e to the power av. Okay, e to the power av. If I take common, so this one actually get cancelled from both sides. If I take them, say this actually, okay, let us just skip this p0 and all. Okay, it will give you better understanding. So let us take ev0 common, this one, e to the power minus av common. So I have got p0 by r minus a v p0 by r. This is equal to 0. So either this will be 0 or this will be 0. So if I put this is equal to 0, then you know this a b has to be infinity. Minus infinity means 0. So I get actually a is equal to infinity, right? From there, sorry, infinity. So infinity I should not take. So I should have another values. Let me see from here. Okay. So if I put this term 0, then I get CP0 by R, A V P0 by R. So this term will cancel each other. So A will be 1 over V. So I get A is equal to 1 over V. So I'll put the value of that A in this expression, in the temperature expression. So expression for the temperature we had got T is equal to P0 V e to the power A V divided by R. Okay, so T max will be, what will be T max? For T max, I have to put the value of A. I have got 1 over V. So P0 V e to the power minus 1 over V. A is equal to 1 over V means e to the power minus 1 divided by R. Okay, I think somewhere I have left one A. I have A over here. Okay, fine. A, yes, fine. So what is the value of temperature? Sorry, what is the value of this? Okay, so P V P0 V E R. Okay, look the options. Okay, we have in terms of A instead of V. Let us put the value of V. Anyway, this will be e to the power minus. So V will be actually 1 over A, right? So I have the values in terms of 1 over. Okay, so in terms of A, so I have to put the value of A. So V is equal to, I'm sorry, we have to put the value of V in terms of A. V is equal to, if I would have put here, let me just put there itself. Okay, this is, see, I'll put the value of V. V means 1 over A. So this is 1 over A, and this will be e to the power minus 1 only. So this is going to be AER. Okay, so what is the value of this T max? T max is P0 by AER. So this is actually the answer. Let us see. T max is equal to P0 by AER. So option C will be the correct answer for this question. Okay, so let us go to the next problem. This is really a very good problem. Let me give you the options for this question first. Let me read the question and then give you the options for this question. So the question says a small square look offside. Square look offside. Achha, offside. This is actually this is offside. A square. This is loop actually, not loop. A square loop. Okay. A square loop. A small square loop offside A and one turn is placed inside a large square loop of side B and one turn where B is much greater than A. That means you have a big square loop like this. Okay, I don't think this is perfect square. Let me just redraw this. This has got greater length. Okay, so this is somewhat square. Okay, this is the bigger square loop which has side B, and inside that there is a smaller square loop, and see the two loops are coplanar with their centers coinciding. So if I say this is the center, so I have got another square loop over here. Okay, another square loop like this. Okay, so which has got, let me redraw this. Sorry. Okay, this is the small loop. Okay, so the centers are actually coinciding. Now if current I is passed in the square loop B, suppose current I is passing through this square loop B, offside B, this is not offside, this is offside B, then the coefficient of mutual inductance between the two loops, then coefficient of mutual inductance between two loops will be, see there are options given over here. Let me write down the options. First option says it is mu 0 by 4 pi B, and in the numerator it is 8 root over 2. Okay, option B says mu 0 by 4 pi into 8 root over 2 B square by A. Okay, option C is mu 0 by 4 pi A 8 root over 2, and option D is mu 0 by 4 pi 8 root over, okay, this is B, 8 root over 2, and in the numerator it is a square. Let us write this as a square by B. Okay, so these are the options. You have to find out which one is the correct option. So whenever we go for calculation of mutual inductance or self inductance, whatever you say, let me clean this portion. Okay, it is looking bad, but anyway, this will be off, this will be off, this will be low. Okay, so whenever we want to find out self or mutual inductance, we should actually find out what is the flux, and flux is actually AMI, mutual inductance, or in case of self inductance it is flux is equal to phi is equal to Li. So if I find out the flux, magnetic flux, then I have to just multiply with I, sorry, divide with I, so that we get the mutual inductance. Rest of the things are easy, right? So how to find out phi? Phi is nothing but B into A. So what is the main problem here? The main problem is to find out what is the magnetic field produced at this center. Let us see, at the center of this square loop. Okay, at the center, and what is this area of the smaller loop. Okay, so magnetic field produced by the bigger loop at the center, and this is the area, A is the area of the smaller loop, that will give you the flux linked with the smaller loop, and that is equal to M into I. From there I will be able to find out what is the mutual coefficient of mutual inductance. Okay, Let us do that. So what is the formula for finding out magnetic field for a finite wire? And this kind of problem you might have done n times. Okay, you have been given a square loop, okay, of some side A. There will be current flowing uh, through the wire of the square loop. Then you have to find out magnetic field at the center of the square loop. So that you know very well, right? So you have to apply the formula for magnetic field produced by a current carrying wire of finite length, and that you know very well. What is that? That is actually mu 0 I by 4 pi A. If the A is the distance from the wire to that particular position, and this will be sine theta 1 plus sine theta 2. Okay, this I know, this is the formula. Okay, for this how I will apply here, let us see this. So this point is actually, see this length, so I have to find out the magnetic field for this particular wire. Suppose we are taking this particular side. Okay, so see this is perpendicular bisector of this angle. Okay, this one. So this will give you the distance from wire to the point. So this distance is actually b by 2, since this is the middle point of the bigger square. Okay, and see this is also perpendicular bisect. This is 45 degree, and this also will be 45 degree, since this is 90 degree. Okay, so I have got here, this is theta 1 and this is theta 2. Okay, so I have got theta 1 and theta 2. So both are 45 degree. Theta 1 equal to theta 2, that is 45 degree. So this part I know then. So mu 0 I by 4 pi. What is the distance? This is b by 2. Okay, write down here. Now this is actually both as theta 1 and theta 2 are both same, and that is 45. So this is now 2 into sine 45 degree. Okay, so this is the magnetic field produced by the single side at the center. Okay, now I have to find out the total magnetic field, and that will be 4 into this b. Then what I get, this is 1 over root 2. So let us write that. So mu 0 I by 4 pi b, and here is 2 that I'll write here 2, and see this is also 2, and this 45 means 1 over root 2, right? So better to go with this root 2 rather than keeping in the denominator. Okay, then we have, see in the options I have 4 pi, so I'm not just striking out this uh, 2 mu 0 and all. So this 4 pi, let us keep like this. Okay, so we have got the magnetic field, see B total, we have got, what is that? That is 2 root 2 mu 0 I divided by 4 pi B. So this we have got. Now what is the flux? Flux will be B total into area of the smaller loop. So smaller loop has area, how much? A into A, area. So it will be A square. Okay, that will be A square. So 2 root 2 mu 0 I divided by 4 pi B into A square. Let us see what we have got. See here, what are the options given? Okay, A square only we have in the last option, and this might be correct except this particular factor. We have to check where we have done a little mistake maybe. Into 4 did I write? No, I haven't written this 4. Yes, so this 4 will come here. Okay, so B total there will be 4. So this will be actually 8. 8 into this. Rest of the things are all right. So this will be 8 square root of 2 divided by 4 pi B means 0 into I. Okay, into A square. So what we get? M will be pi by I. So divide this I. Okay, so I have got 8 root over 2 means 0 A square divided by 4 pi B. So in terms of okay, so this has got nice arrangement of this factors. Okay, let me write me 0 by 4 pi, then 8 root over 2 and A square by B. Okay, look this fourth option. So this is actually correct answer for this question. Okay, all right, so we have got the answer for this. D will be the correct answer. So here the bottom point is that whatever for whatever geometry or whatever loop it may be, if you want to find out what is the mutual inductance or self inductance, you have to find out the flux linked with that. Okay, flux linked with that, and then once you get the flux, you have to divide that flux with the current. Okay, that will give you the answer. Okay, so let us solve this problem. This problem is also going to be a very interesting problem. This is from dimensional analysis. So the question says, which of the following equations is dimensionally incorrect? Where t is the time, h is the height, s is the surface tension, theta is the angle, p is the density. Sorry, this will be rho. Rho is the density, and r is the radius, g is the acceleration due to gravity, v is the volume, p is the pressure, w is the work done, tau is the torque, this is permittivity, and E is the electric field, and J is the current density, L is the length. And let me give you the equations here. So what are the equations given? So W is equal to tau theta. Okay, first one. Second one is B, that is H is equal to 2s cos of theta by rho r and g. Okay, then option C, V is equal to pi I think this is P given here. Okay, P or rho. Let me, I think it is rho over here. Rho e to the power 4 divided by 8 eta L. And option D is J is equal to del E by del T. Okay, we have to find out the answers for, like we have to find out the incorrect option here in terms of dimensionality. You have to check. See, this is tau. Tau is the counterpart of, not counterpart, it is the what is that called? force equivalent in the rotational mechanics. So work done in case of translational motion, force into displacement, right? So here theta is the angular displacement and tau is the force equivalent in the angular motion. So this is actually work done, this is true. See this expression, this is actually capillary rise. If you remember, this is H is equal to S cos theta by rho r G. This is also all right. Capillary rise. So if you want to capillary rise, sorry, rise, capillary rise. So this is also will give you the height. Okay. So this is also correct. Let me see this one, then I'll see the last one. So J is the current density, it is said, right? Current density means current by area. Current by area, that means, you know, this current by area is the current density. Okay. So current has got, see, current has got unit, how much? Or dimension. Let us write that V by R, maybe. Okay, that I can write if I want to write. Okay. Or I can write this I as Q by T. Q by T. Okay, so I can write Q by T. Current has got unit actually ampere by meter square. Okay, ampere per meter square. But what is this unit? This is volt, or this electric field is actually has got unit Newton. See, F is equal to QE, right? E is equal to, so Newton per coulomb. Newton per coulomb, and this is T. So Newton per coulomb means force, unit of force divided by charge into time. Force, see, force, unit of force divided by charge into time. Okay. Charge into time. So in case of this current density, actually we don't get force and all. So current divided by area. Okay. So it seems to be wrong. Okay, this seems wrong. Let me confirm you. Let me confirm you. What is this? Okay, I think there was one more thing here. Okay, that's why I am. Okay, there was epsilon over here. Okay, then it is correct actually. Epsilon, yes. So this will give you the density. So this is current density. This is for CO. So this is for current density. We know this is for current density. Okay, this is fine. Now it is all right. Epsilon naught into. Okay, so we know electric flux by tau. time into epsilon naught or epsilon whatever. This gives you displacement current. Okay, when you multiply this phi is equal to E into A and divide that, so I'll get J is equal to epsilon naught del E by del T. So I don't need to do this further since I remember the expression. So this is also correct. So this must be then incorrect. So the answer will be this C. Okay, dimensionally incorrect it is said. So dimensionally incorrect will be which one? The first option itself. Okay, I'm sorry, this option C itself. Okay, so option C will be, see, since all three are all right, or by logic it should be incorrect. Okay, this should be incorrect, so you don't have to go for further direct analysis. So this will be incorrect. Indirect analysis says that this will be wrong. Okay, so with this I'll stop it here for today. In the next class we'll take the second shift of this particular paper, then we'll go for the discussions of the recent papers of 2024. Whatever papers we will get available, we'll take up and try to solve one by one. Okay, so but before that I'll finish this shift 2 paper also. Okay, so thank you for your patience. Bye for today.